In 1950, a British mathematician published a paper in a philosophy journal called Mind. The paper presented a profound, challenging philosophical argument about machine intelligence, but hidden deep inside that theoretical argument was something entirely different. It was a precise, albeit speculative, hardware specification for a future that did not yet exist.
That mathematician, of course, was Alan Turing. He estimated that to build a machine capable of playing his imitation game, what we now call human-level artificial intelligence, you would need a storage capacity of about 10 to the ninth power binary digits. Translated into modern terms, he asked for about 125 megabytes of memory, and he boldly predicted humanity would have that computing capacity within, quote, about 50 years.
To put that enormous request into perspective, look closely at what actually existed. The world's very first stored program computer had started running in June of 1948, just 2 years prior. Do you know how much memory that machine actually held? Exactly 1,024 bits. Not megabytes, not kilobytes. Exactly 1,024 individual bits.
So Turing is standing in a room with a machine holding roughly 1,000 bits and casually writing an academic paper that assumes a future machine holding 1 billion bits. That is an enormous conceptual leap. He was projecting a computational future nobody on Earth could build yet, assigning a massive physical number to a machine that simply did not exist.
Which brings us to the central, driving question that starts this entire season. If Turing's basic idea was roughly right and his timeline of 50 years was surprisingly accurate, what actually happened in the middle? If the theoretical idea was already there on paper, what actually took 50 years to build?
Quick note, this is education, not advice of any kind. AI moves fast, so treat it as a map, not gospel, and go try it yourself.
Welcome to the Working Thesis. I am Maya.
And I am Theo. This season, we trace a series we call AI History, how ideas and silicon built each other.
This is a history series, but we must say right up front that the point of this show is not just a chronological list of milestones. The point is to understand a specific, relentless loop that drove the entire industry forward. We want to show you the engine, not just the milestones.
Right. The loop works like this. First, a new idea about machine intelligence appears. But an idea alone is never enough. The immediate, practical question becomes, can our current hardware actually test this idea? If yes, the hardware runs the test, and the real-world evidence reshapes the idea itself.
Once you have solid evidence that an idea works, that evidence attracts money. That money funds the expensive engineering development of much better, much faster hardware. And once you have better hardware, suddenly much bigger and far more complex ideas become testable. And then the loop repeats. Idea, testability, evidence, money, better hardware, bigger ideas.
Today, in episode 1, we are looking at the very first turn of that loop. We are looking at a unique moment in time when the idea was emerging, but nobody on Earth could complete the circuit. The hardware simply could not test the theory. The machine was not ready to meet the mathematical imagination. We are talking about a world where computers filled entire rooms but possessed less memory than a modern pocket calculator.
And as we will see, this dynamic builds toward a very practical problem. When you are standing in the middle of that gap, when the idea exists but the hardware does not, how do you tell the difference between an idea that is completely wrong and an idea that is merely early? Let us go back to that 1950 paper. What exactly was Turing proposing? He proposed something he called the imitation game.
The setup was simple, but profound. You have an interrogator communicating by teleprinter, a text-only interface, so physical appearance and voice are completely hidden. The interrogator asks questions, trying to tell a human from a machine after 5 minutes. If the machine successfully fools the interrogator, it wins.
But here is the crucial philosophical detail. Turing deliberately set aside the question, can machines think? He wrote that he considered that specific question too meaningless to deserve discussion. It was too ill-defined, too tangled in human emotion to ever settle. So he replaced it with something measurable.
And there are 2 things worth correcting here, because popular history usually gets them wrong. First, Alan Turing never actually wrote the phrase Turing Test. He exclusively called it the imitation game. That famous name was attached later.
Yes, and correction number 2 is even more important for understanding his rigor. His bar for success was that the interrogator have, quote, not more than 70% chance of correct identification. It was not a 50-50 coin flip, which is what almost every popular account says. He set a specific, testable statistical threshold.
It is humbling that the single most famous test in AI history is usually described completely wrongly. He was a mathematician, and his test was mathematically precise. He wanted to strip away the endless, circular philosophical debates and focus entirely on observable output.
But to understand how he even conceived of this, we need a brief detour to 14 years earlier. In 1936, Turing introduced the concept of the universal machine, a single machine that could simulate any other machine, as long as it was given a description of it.
Exactly. Before that, machines were built for one specific task. To change the task, you had to physically rebuild the machine. Turing's 1936 paper, originally about computability and the limits of what can be computed, separated the algorithm from the physical device.
That separation is the absolute precondition for this entire series. It meant you could change what a machine does without rebuilding it, making the loop between software ideas and hardware possible. It was not an AI blueprint, but it was the foundation that made later ideas conceivable. So where does this massive hardware specification actually come from? The 10 to the 9th power number does not appear in his description of the game itself. It appears much later in the text, while Turing answers potential objections from theoretical critics.
Right? He anticipates people will argue machines could never be kind, resourceful, beautiful, friendly, or funny. His counter-argument is brilliant. He says, many of these limitations are associated with the very small storage capacity of most machines. He argues that the perceived lack of humanity is actually just a lack of memory.
We should note, honestly, that those two famous passages, the imitation game itself and the memory estimate, are in completely different parts of the paper. They are not sitting side by side, but they are part of the exact same continuous thought process.
He was not writing an algorithm yet. He was pricing the machine that an idea would need. He was calculating the physical cost of simulating human-level conversational variety. And he hedged deliberately, stating no mathematical accuracy was claimed for his estimates. He knew he was sketching a rough boundary.
But even with that hedge, Theo, this is a massive historical milestone. This is the first time anyone attached a specific numerical hardware budget to the abstract idea of machine intelligence. He anchored abstract philosophy to concrete hardware.
Exactly. He said, if you want to do this, here is roughly the size of the bucket you will need to hold the necessary complexity. And that bucket was astronomically larger than anything that existed on Earth. He essentially said, before we can even debate algorithmic elegance, we must build a physical container capable of holding 1 billion discrete states. The philosopher was thinking like an engineer.
Let us talk about exactly what did exist on Earth at that moment. We have to keep 3 specific machines distinct here, because popular accounts constantly merge them together into one mythical early computer. We need to be precise.
First, there is the Manchester Baby, which ran in June of 1948. It held exactly 32 words of 32 bits each. That is exactly 1,024 bits. That is the baseline for the very beginning of stored program computing.
Second, there is the Manchester Mark I, which ran across 1949 and 1950. This machine had about 5,120 bits of fast cathode ray tube store, plus a magnetic drum for slower storage. And this is the crucial point. This is the machine Turing was actually using while writing his paper.
We should note that memory in this era was intensely physical in a way that is hard to imagine now. Turing had previously worked on a different design called the ACE, which planned to use sound pulses circulating in tubes of liquid mercury, while the Manchester machines he actually used stored charge patterns on the glowing phosphor of television-style screens. They were completely different machines with different memory technologies.
And third, just for historical completeness, there was the Ferranti Mark I in February of 1951, which bumped the fast store to about 10,240 bits, along with a much larger drum.
Turing wrote in that exact same 1950 paper that he had set up a program on the Manchester computer using, quote, only 1,000 units of storage. He was not speaking theoretically about computers. He knew this hardware intimately because he was literally programming it with his own hands.
Let us do the arithmetic out loud. Against the baby's 1,024 bits, a billion bits is 6 orders of magnitude away. Against the Mark I's fast store, which he was actually using, it is roughly 200,000 times larger. The gap is breathtaking.
And we should be careful here. We cannot call the Manchester machine the biggest computer in Britain because Cambridge's EDSAC was also running at the same time. But we can confidently say it was one of the largest machines then operating anywhere in the world. And for this task, it was hopelessly, completely too small.
This is where I want to slow down, because it is easy to describe this gap between idea and machine in a way that is subtly wrong.
Yes, the temptation is to look back and say, Alan Turing had a finished algorithm and was just sitting there waiting for faster chips. But that is false. In 1950, there was no training method, no massive dataset, and no learning architecture in the modern sense.
What actually existed was a testable behavioral target, the imitation game, and an educated estimate of the massive memory that target would ultimately require.
So the honest historical framing is not a finished idea blocked by slow hardware. It is an idea still forming, which hardware could not yet test. The gap was both conceptual and physical at the exact same time. The software and the hardware were both missing.
But wait, there is another quote in that same 1950 paper that sounds incredibly modern. In a later section on learning machines, Turing wrote, verbatim, "Instead of trying to produce a program to simulate the adult mind, why not rather try to produce one which simulates the child's? If this were then subjected to an appropriate course of education, one would obtain the adult brain."
It is a brilliant intuition. It shows he did not just propose a test. He proposed learning as the route 5 years before the term artificial intelligence was coined.
It sounds exactly like modern machine learning.
It sounds like it, yes. But look at the massive gap between the intuition and the method. He had the idea and mused about education, punishment, and reward, but could not specify a working mechanism. There was no training algorithm, no dataset, and no way to run it.
So this actually strengthens our point. The seed of machine learning is right there in 1950, but it is still only a seed. It is a direction, not a blueprint.
I can hear a listener objecting right now. So was Turing just guessing about the memory requirement? Was he just throwing a giant number at a wall?
Not at all. He was reasoning rigorously from what a machine would logically have to store to mimic human linguistic variety. He knew how much data it takes to represent basic rules and extrapolated outward. It was an educated, grounded estimate from a mathematician who knew exactly how rapidly complexity scales up.
So the idea is emerging. The hardware is inadequate, and nobody knows exactly how to bridge the gap. That is the landscape in 1950. The loop is stalled before it can even really begin. You have visionaries staring at machines that fill entire rooms but possess less memory than a modern greeting card.
Let us jump forward 5 years to a famous proposal dated August 31st, 1955. It was formally submitted in early September, and it came from 4 brilliant men: John McCarthy, Marvin Minsky, Nathaniel Rochester, and Claude Shannon.
This document contains a deeply famous opening line. We propose that a 2-month, 10-man study of artificial intelligence be carried out during the summer of 1956.
And that document is where the term artificial intelligence gets its very first formal use. John McCarthy reportedly chose that specific phrase partly for its neutrality, wanting to avoid getting tangled up in existing, highly charged debates about automata theory or cybernetics.
The conjecture they proposed to work from was incredibly bold. They wrote that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it.
The ambition is staggering when you read it today. 10 people, 1 single summer. And they list their goals, which included making machines use language, form abstractions, and, crucially, improve themselves. They genuinely thought they could make a significant dent in all of this over a summer vacation.
We should note gently that while the workshop itself happened in 1956, the proposal was written in 1955. Popular accounts often merged the proposal and the event, but the core thinking was crystallized the year prior. They were laying out the roadmap for a field that did not yet fully exist.
There is one specific sentence in that 1955 proposal that I want to read in full, slowly, because the entire premise of our series turns on it. It is right in section 1.
Let me read it. The speeds and memory capacities of present computers may be insufficient to simulate many of the higher functions of the human brain, but the major obstacle is not lack of machine capacity, but our inability to write programs taking full advantage of what we have.
Let us unpack that carefully. They saw the hardware gap. They explicitly named the limits of speed and memory, and then they explicitly, consciously ruled it the lesser problem.
We need to be fair to them. Programming ability really was a massive bottleneck in 1955. They were dealing with primitive programming environments. They were absolutely not wrong that software and programming theory mattered.
But the weighting was backwards. They bet code was the main obstacle, and the next several decades would be spent discovering that it was both. Hardware was not just a secondary detail, it was a fundamental ceiling no amount of clever code could bypass.
I look at this as the founding document of the field betting against hardware put down in writing. They planted a flag saying software was the primary hurdle.
But Theo, is it fair for us to judge them with 70 years of hindsight? They could not possibly know what billions of parameters would require.
I concede that point partly. It is easy for us to sit here in 2026 and call them overly optimistic. But the reason this sentence still matters so deeply is because the entire field acted on that weighting. They organized decades of funding and research around the assumption that clever programming could overcome limited memory. It created a paradigm where hardware was viewed merely as a passive vessel. This miscalculation shaped research priorities for a generation. It took decades of painful stagnation to realize that without massive computational power, even the most brilliant algorithms were effectively paralyzed.
This raises a natural question. Did Turing, or the Dartmouth group, or the researchers we are about to discuss, invent neural networks? The answer is no, but the idea was already circulating around them.
Absolutely. The Dartmouth proposal's section 3 is literally titled Neuron Nets, and it explicitly asks how a set of hypothetical neurons could be arranged so as to form concepts.
That section cites existing work by Pitts and McCulloch, Farley and Clark, Utley, Reshevsky, Minsky, Rochester, and Holland. So this was already a very live, active research thread. It was not a brand new proposal generated out of thin air for the summer camp.
The real origin goes back earlier. Warren McCulloch and Walter Pitts published their artificial neuron model in 1943. That is, before Turing's 1950 paper and long before the Dartmouth proposal.
Turing himself had independently sketched what he called unorganized machines in a 1948 report. He described B-type machines with modifiable connections, which we now read as a clear precursor to neural networks.
But here is the catch with Turing's 1948 report. It stayed unpublished for about 20 years. It influenced almost nobody at the time. It is an independent anticipation, but it is also a perfect example of a brilliant idea simply sitting in a drawer, completely disconnected from the loop.
The honest conclusion is that the Dartmouth conference convened and named a field that already contained the neural network idea. It did not originate it.
And here's a hook for our next episode. The Dartmouth proposal describes Marvin Minsky as having built a machine for simulating learning by nerve nets, and having written a thesis called Neural Nets and the Brain Model Problem. Note that carefully. This same Marvin Minsky later co-writes the critique that helps freeze neural network research for years. We will dive deep into that historical irony in episode 2.
I want to look closer at one of those 4 Dartmouth authors, Nathaniel Rochester. He is fascinating because he straddles the exact line we are exploring in this series.
Rochester was jointly responsible for the design of the IBM 701 computer. And the Dartmouth proposal also notes that he worked on simulating nerve nets, using computers to test theories in neurophysiology.
So one of the 4 founding authors of the proposal sat on both sides of this series loop. He literally built the physical hardware, and then he turned around and used it to test a brain-inspired idea.
This is exactly why the Dartmouth hardware sentence we read earlier is not just naive optimism. The people who wrote that sentence knew exactly how much compute existed in the world, because one of them literally designed it. They understood the physical constraints deeply.
It also shows the real, uncompromising constraint of the era. The neural net idea could be simulated, yes, but only at whatever tiny scale the physical machine allowed. Rochester's simulations were bounded by the very architecture he helped create.
He could not outprogram the physical limits of his own invention. The hardware set the absolute boundaries of the mathematical imagination. Every theoretical leap Rochester wanted to make in simulating neural pathways was immediately yanked backward by the physical reality of the circuits he himself had soldered together.
While Dartmouth was being planned, another researcher was dealing with these exact physical limits. His name was Arthur Samuel, and he wanted to build a checkers program strong enough to show the world what electronic computers could really do.
Samuel started his work at the University of Illinois, but the work stalled. If you read his IEEE biography, it says the program was, quote, not finished while he was at the University of Illinois, perhaps because the computer was not finished in time.
That machine was the Iliac, which was a project Samuel himself had helped start. Just sit on that sentence for a moment. The program was late because the computer was late. The code was waiting for the silicon.
He ended up joining IBM in 1949, moving toward the engineering lab that was building the IBM 701. He went to where the hardware was actually being finished.
The obstacle here was not a missing philosophical insight. It was not a lack of clever code. It was a literally incomplete machine. He was waiting for the vacuum tubes to catch up to his intention.
He knew exactly what he wanted the machine to do, but he had to wait for the machine to exist. The idea was ready, but the physical world was not.
Once Samuel finally got access to the IBM 701, he faced a brutal reality check. The IBM 701 offered 2,048 words of 36 bits each.
Let me emphasize that. Words, not bits. 2,048 words of 36 bits each. That gives you roughly 73,728 bits of fast memory.
To make that relatable, that is about 9,200 bytes, roughly 9 kilobytes.
Exactly, 9 kilobytes. That is less memory than a single modern text message thread, or a fraction of one low-resolution photo. And that was the pinnacle of fast memory at the time.
The game of checkers has vastly more possible positions than that. Storing the full game tree or searching the entire game tree all the way to the end of a match was simply mathematically impossible on that machine. There was no amount of clever coding that could bypass that physical fact.
So Samuel had to get creative. He used a technique called alpha-beta pruning. Imagine you are walking through a massive maze. If you look down a hallway and immediately see a dead end, you do not keep walking down that hallway to see exactly what kind of dead end it is. You just turn around. That is pruning. You stop exploring a branch of the game tree once you know it cannot possibly change your final decision.
Because he could not search to the end of the game, he scored intermediate board positions. And then he let the program adjust those scores based on its own experience playing the game.
He also used rote learning. The program would remember board positions it had already evaluated, explicitly trading his incredibly scarce memory against the cost of doing repeated computational work.
And here is the part one find genuinely striking, stated as plainly as I can. The memory limit of the IBM 701 did not merely delay Samuel's program, it selected his method. Samuel could not brute force the game of checkers, so he was forced to invent something that worked without brute force.
And that method, learning a scoring function and improving it from your own play over time, is a direct, undeniable ancestor of self-play reinforcement learning. That is the exact same conceptual family that machines later used to master the game of Go.
That is incredible. The physical constraint of the machine actually produced the much more general, much more powerful idea. If he had infinite memory, he might have just brute forced it. The hardware limit forced the innovation. Samuel's checkers program eventually reached a televised demonstration, reportedly on February 24, 1956.
And Thomas J. Watson Sr., the head of IBM, reportedly remarked that the demonstration would raise the price of IBM stock 15 points. And it did. The loop was turning. Evidence of success was attracting money and market value.
In 1959, Samuel published a landmark paper whose title contained the specific term machine learning. It is widely credited as the first published use of that exact phrase.
Though there is a myth attached to him, people constantly quote Samuel as defining machine learning as giving computers the ability to learn without being explicitly programmed. That phrasing does not actually appear in his writing. It is a paraphrase that hardened into a quotation.
Fast forward to roughly the year 2000. By that time, ordinary personal computers were finally shipping with about the amount of memory Alan Turing had specified in 1950. His 50-year estimate held up beautifully.
Which tempts you into a tidy conclusion that the ideas were all finished by 1959, and the world simply waited 50 years for the hardware to catch up. I do not think that is true, and it is worth resisting. A checkers program that tunes a scoring function is a long, long way from a general theory of machine learning.
So if I had to put it in one line, the ideas were still emerging and incomplete, the hardware could not test them, and the limits of that hardware helped decide what those ideas ultimately became.
And that brings us to episode 2. Because once hardware cannot test an idea, that idea starts to look simply wrong. And the entire field is about to spend 20 years learning exactly how expensive that confusion is.
See you next time. That's a wrap. If this made AI a little clearer, hit subscribe. It helps more curious people find the show. See you next time.